Hello and welcome to our second devlog. So the other evening, me and Matthias were working on our project and we encountered an interesting bug related to trying to access unaligned data. And I'd never dealt with an issue like this before, so I learned a lot just going through it with Matthias, and I just wanted to kind of explain what we did and how we did it, what we did to solve it basically, and how we did that. And just basically for learning consolidation for myself as well. So basically what happened was we had mainly been running the project in debug mode, and the other evening we tried running it in release mode, and this crash happened that you can see here. So this error code is, you can see at the end, a general protection fault error, which can happen for a number of reasons. However, we had also previously run the program in debug mode with the address sanitizer, and it had been showing some warnings related to access of unaligned memory, but we hadn't done anything about that yet. We had just left it as something to deal with at another point. So it seemed like that could be the issue causing this general protection fault in release mode. So we decided we needed to fix that problem anyway, so we might as well fix that, and then we would find out if it was also causing this issue here. So I'm first going to do a basic overview of what data alignment even is. So what is data alignment? So your computer really likes to access data on what's called a natural alignment. And a natural alignment of a data type is usually the size of that data type. So for example, for a 4-byte integer, its natural alignment would be 4 bytes usually. And so when your computer needs to access, for example, again, a 4-byte integer, it wants to access that int on a 4-byte boundary. In other words, it wants to access the int at a memory address that is divisible by 4. So I'll just draw a quick diagram as an example. So this is just a section of memory, and it continues, either side, but we just picked out a section, and these numbers in the boxes are our memory addresses. So here, when your computer needs to access this 4-byte integer that we have, it wants to access it on a 4-byte boundary, so that would be either address 12 or address 16 in this case. So these are all multiples of 4. Okay, and if it can't do that, this is when we get the general protection fault that we saw earlier in some cases. So we're now going to have a look at the Intel manual just to read a bit more about this. So we can get more information about this sort of thing from the Intel Software Developers Manual. So I just wanted to come here and look at this because I found it quite interesting. And in the manual, under this section, alignment of words, etc., there's a bit more information on this. So words, double words, and quad words do not need to be aligned in memory on natural boundaries. The natural boundaries for words, double words, and quad words are even number addresses. Addresses evenly divisible by 4, blah, blah, blah. However, to improve the performance of programs, data structures, especially stacks, should be aligned on natural boundaries whenever possible. The reason for this is that the processor requires 2 memory accesses to make an unaligned memory access. Aligned accesses require only 1 memory access. A word or double word operand that crosses a 4-byte boundary, etc., is considered unaligned and requires 2 separate memory bus cycles for access. Then there's an extra bit here. Some instructions that operate on double quad words require memory operands to be aligned on a natural boundary. These instructions generate a general protection exception if an unaligned operand is specified. Other instructions that operate on double quad words permit unaligned access without generating a general protection exception. However, additional memory bus cycles are required to access unaligned data from memory. Okay, so there's two things to mention here. So the first thing is this bit that it mentions here about some instructions require memory operands to be aligned on a natural boundary. So that's what happened in our case, basically, is when we were in debug mode and we didn't get the general protection fault, it's because the compiler was generating instructions that didn't require the data to be aligned. And when we were in release mode, the compiler optimized the code and generated instructions that did require the data to be aligned. And when it wasn't aligned, we got the general protection fault. So for example, two of these instructions are, so one of them is movups, which moves 4 unaligned packed single precision floating point values between registers or register memory. So this instruction can deal with unaligned values. And this is the instruction that we were getting generated, that we were using in debug mode. And then it's actually just here, in release, instead of movups, the compiler was generating code that used movups, which is move 4 aligned packed values, blah, blah, blah. So in release, we were using the instruction that required the data to be aligned, but it wasn't aligned. And I just want to go back again. So let's see, to that section we were at before. Alignment of words. So one other interesting thing to mention is in this paragraph here, where it mentions to improve performance, data structures should be aligned on natural boundaries, and the reason for this is that the processor requires 2 memory accesses to make an unaligned memory access. So we then looked into this uops site here for just to see what the difference was in speed between using movups, which is the aligned instruction, or movups, which is unaligned. So according to the Intel document, you would think that movups would be slower. Where is it? Here. Oh yeah, movups would be slower. But actually, when you look on here at the latency and throughput, it's exactly the same. So for movups, for 11 and 0.5, and for movups, for 11 and 0.5. So we don't really know why that is, and if anyone watching this knows why, it would be interesting to know why it doesn't actually seem to be slower. But yeah. Okay, so this is our program running in release mode, and this is where the crash happens. And you can see that the crash happens when it's trying to do this movups operation. And movups, as we just saw, we can only use that on aligned memory, and our memory is not aligned. So why that's happening in our program is, usually, basically, when writing C++ code, this issue wouldn't be a problem, because if you're using any of the expected ways to allocate memory in C++, such as using malloc or new, then C++ will make sure that data is aligned to 16 bytes, which should cover most cases. However, in our program, let's get rid of this, we have 2 custom allocators that we use. And one of the allocators, this per frame allocator, the way that works is it allocates a large block of memory at the start of the program, and then every frame, when we need memory for something, we use a chunk of that memory that we allocated right at the start. However, this per frame allocator doesn't align the pointer it returns. So basically the pointer can be pointing at memory or can be pointing at address anywhere inside that big chunk of memory. So for example, I will just draw a quick diagram. So our per frame allocator, right at the start of the program, let's say it allocates this much memory, and all the boxes are different addresses, and let's say 1, 2, 3, 4, 5, 6, 7, 8, etc. And then in the frame, when we want to use some of that memory, we get a pointer to an address in the memory, but we don't make sure that it's aligned. So it could be pointing at address 6, and we're trying to align. We want memory for an integer on a 4-byte boundary, and that's not going to work. So that's why we're getting this issue in our program. Okay, so now we know what the issue is. How do we solve it? So I'm going to go through what we did to fix this issue. So the first thing we need to figure out is how much memory we actually need to allocate. So we have our data. So let's say our data is data is an int of 4 bytes. So let's say we'll call this our desired, we'll call it our data size. Let's see. Data size is equal to 4. And then we also have our alignment, which is also going to be equal to 4, the same size as the data type. So when we ask for some memory to be allocated, let's imagine we receive a pointer to, I'm just going to draw some addresses here. And let's say in these boxes we have address 8, so obviously there's address before this and after. I'm just picking out a little section. And these are all our addresses. And let's say we ask for some memory to be allocated, and we get the memory allocated, fine, and we receive a pointer to that memory. And the pointer is pointing at address 8. And address 8 is divisible by 4, so it's aligned on a 4-byte boundary. So that's fine. We can put our 4-byte in here, and that's fine. So that's the best case scenario, is that we receive a pointer to our memory, and it's aligned to the natural alignment boundary that we need it to be aligned to. But we need to consider the worst possible scenario too. So worst scenario is we get a pointer back to the memory, and it's pointing at address number 9. This is not aligned to a 4-byte boundary, so we have to keep going until we get to an address that is aligned to a 4-byte boundary, which is 12. So we have to move up 3 bytes to address number 12. So in this scenario, and then we move up to 12, and then we can actually put our int here. So in this scenario, we need the 4 bytes for our int over here, but we also need these 3 bytes at the start, which we're not going to do anything with them, they're just going to be padding. So in total, for our worst case scenario, we need the data size, which is what we've got here. We've got our data in here, plus the alignment minus 1. And so if we use this calculation, we'll always have enough enough memory allocated that we will be able to align our data. So we now know how much memory we need to allocate to ensure that we'll be able to align our data. So that's step number 1 that we've just done. So the next step is to actually allocate that memory. So then, for example, we will get a pointer to that memory back, and let's say again that we're wanting to we want to allocate space for a 4-byte integer, and let's say we get back, in this case we would get 4 plus 4 minus 1, we would get 7 bytes. So let's see, 6, 7. And let's say 9, 10, 11, 12, 13, 14, 15. Let's say we get these 7 bytes back and our pointer is pointing here. So we've got enough space, but our pointer to the memory could be pointing to an address that isn't aligned still. So now the next step is to calculate by how much we need to offset. By which I mean, like here, you would need to offset by 3 bytes. So we get up to, so we move our pointer to point up 3 bytes up. Okay, so I'll move somewhere else to go through how we do that. So I'm going to outline 2 ways that we could do that. So when we allocate some memory, we will get back a pointer to that memory address. So let's say we have our pointer to the memory, my pointer. We now want to get the numerical value of the address that our pointer is pointing to, and we can do that by casting our pointer to size t or pointer diff t. So let's see, pointer diff t, we'll call it pointer value is equal to pointer diff t my pointer. So we now have the numerical value of the address that our pointer is pointing to. So if we now get that value, and let's just pretend for this example that pointer value is address 9. So we're pointing to address 9. And if we get that value and we modulo it with the alignment, so I'll also write this over here. So let's see, oh no, I want it to have it in blue. Let's cross that out. Let's see, pointer value is 9 and our alignment is 4, because we're still using the 4-byte int example. So if we get our pointer value and modulo it with our alignment, so 4 goes twice into 9, and then you have 1 left over, so we are left with 1. And then we can do our alignment, which is 4 minus this value here, so minus pointer value modulo alignment. So 4 minus, oh, I wanted to do that in blue. So 4 minus 1 is equal to 3. So we get our offset of 3, which is, as we saw in our previous diagram, that's what we need. If we are given the address of 3, we need to move, of 9, sorry, we need to move up by 3 to address 12. So this is our calculation. This is the first calculation that we could do to get the offset. So offset is equal to alignment minus pointer value modulo with alignment. Now this is fine, but the modulo operation is relatively expensive, and especially if we're going to be doing this operation a lot at runtime, if we can find a more efficient way to do it, that would be great. So there is another way we could do the same thing. And for this option, we first need to understand some properties of binary numbers. So another thing actually that we need to know is our alignment number is always going to be a power of 2. And in a binary, powers of 2 always have just one bit set. So for example, we'll do decimal, binary, and we'll go for our powers of 2. So 2 to the power 1 is 1. Sorry, 2 to the power 0 is 1, sorry, 2 to the power 1 is 2, etc. 8, so we'll just do these. So, and in binary, 2 in binary, 4 in binary, and 8 in binary. So you can see in powers of 2, we just have the 1 bit set. Okay, the second thing that we need to know is what happens when we minus 1 from any of these powers of 2. Something interesting happens. So again, I'll do decimal and binary. So for example, we'll use number 4. So 4 in binary 0, 1, 0, 0. And if we do -4 minus 1 is 3. And in binary it's 0, 0, 1, 1. So you might notice that this bit that was set here in 4 is unset in 3. And these two bits that are unset in 4 are now set in 3. And we'll just look at one other example, 8. So 1, 0, 0, 0. And if we do 8 minus 1, we get 7. And in binary, 7 is 0, 1, 1, 1. So the same thing has happened. This bit that was set is now unset. The bits that were unset in 8 are now set in 7. Okay, so we can use this to get a sort of a different way to do a modulo. Okay, so we're now going to do something using those properties. And one thing we need to know is that our pointer value is always going to be bigger than our alignment, and that our alignment is always going to be a power of 2. So let's imagine we have a pointer value of 15, which in binary is 1, 1, 1, 1. And let's say we have an alignment of 4. And in binary, that's 0, 1, 0, 0. So we need to figure out how many times our alignment goes into our pointer value, and then what the remainder is from that, basically. Now, with our alignment, we always have the 1 bit set, 'cause it's always a power of 2. And with these powers of 2, for the values on the right-hand side of our bit, and the bit itself, you always know that that number is going to go into the numbers, both itself and the numbers on the on the left-hand side, not the right-hand side. On the left-hand side, is going to go into those numbers fine, with no remainder, basically. However, it will not go into the numbers on the right-hand side of the bit that we have set for the alignment. So if we could set these bits on the right-hand side, and do a bitwise and of those bits, of these bits on the right hand side with our pointer value, that would tell us the remainder, because if the pointer value has any of those bits here in common, it will basically tell us that our original alignment number would not have been evenly divisible, and this is the value that is left over after you have gone into that number however many times. So what is one way that we could set these bits and unset this? Okay, we just looked at it over here. So we could do alignment -1. So if we do our pointer value bitwise and with our alignment -1, it's basically the same as what we did earlier in our, where do we do? Oh, it's just here. Yeah, it's basically the same as what we did here, pointer value modulo alignment. So it basically tells us the same thing. So I'll just do one little example using this this pointer value 15 and alignment of 4. So let's say we have we'll do our alignment -1. So 4 minus 1 is 3. So in the rubber. So alignment -1 is 3. So 0, 0, 1, 1. And we're going to do a bitwise and with 15, so 1, 1, 1, 1. So I'll just do that. So bitwise and 0, 0, 1, 1. So our offset is equal to 0, 0, 1, 1, which in decimal is 3. And is that correct? Yes, 4 goes into 12, and then we have 3 left over. So this here is just a more efficient way to do this operation. Yep. So we can add that. Where do we have? Oh, and of course we need to also do alignment minus this. So it would be alignment minus the pointer value bitwise ANDed with alignment -1. So we'll just do that. Calculate by how much we need to offset. So we will have our offset is equal to the alignment minus pointer value ANDed with alignment -1. So in that example that we just had there, we would have had an alignment of 4 minus, and our pointer value was 15. We ANDed it with alignment -1. And what did we get? We got 3. So our offset would be 4 minus 3. So our offset would be 1. And yeah, so we had our pointer value, and then we would have to offset it by 1, so bump it up to 16, and then we would be aligned on a 4-byte boundary. So all good. Okay, so now we have the offset, and we can bump our pointer up to point at that address, the aligned address, and we can put our data there. So that's excellent, everything is aligned, and maybe that's the end of it, but not quite. We have another issue that we need to deal with. So we'll call this section here our allocating and aligning, and that's all good. But one problem is that when we allocated our memory and we got our pointer to that memory, let's say at stage 2, right? Let's say we got that memory and it was here, 9 to 11, 12, 13. And it was originally pointing to address 9. And we wanted to allocate memory for an int, so we needed to have it at address 12. So we put our int in there, and our pointer is now pointing to address 12. This is an issue when we then come to free that memory, because we need to deallocate from address 9 because that's what the OS gave us. But how do we do that when the pointer is now pointing to address 12? So one way we can do this is that when we get the offset amount here, originally when we're allocating and aligning, we can store that offset amount in one of our empty bytes one of our empty padding bytes, like we could store it here, for example. And then when it comes to freeing, we can go back 1 byte, check the amount that's in that byte. So here, in this byte here, we would store the number 3. And then we can check that byte, and then we can move our pointer back by 3 bytes, and we'll be pointing at the start of the original memory. So that's how we'll solve that issue. So now I'm going to go over and start actually implementing this solution in our code. Okay, so we're now going to actually implement our solution in the code. So in our program, we have 2 custom allocators. One is this per frame allocator, which inherits from allocator here and has these 2 virtual functions. And the other one is OS memory allocator, which we'll look at after. We're going to look at per frame allocator first because that's where our issue is actually coming from. So how our per frame allocator works, I mentioned a bit earlier, but basically at the start of the program, we allocate a big chunk of memory, and then when we need to use some of that memory, in this allocate function, we come and ask for a pointer to a part of the memory. So what it basically does here is it has this buffer watermark that is keeping track of where it is in the big chunk, basically. And then we cache this buffer watermark at the start of this function into offset. Then we increase the buffer watermark by whatever size we want for our current piece of data. And then we get a pointer back of the frame memory buffer plus the offset. And then, so we'll get a pointer to the start of that memory. And we then set all the memory between that pointer plus size bytes to 0, and then we return a pointer to the start of that memory. But the problem is that this pointer might be pointing a memory that's not aligned, so that's what we need to fix. So we'll start by passing in a new parameter, alignment. Right. So here we don't actually need to allocate any memory because it's already been allocated in that big chunk at the start, but we need to make sure we're asking for a big enough amount of memory that we can then align the data within that. So we need to change this size. So if we do our size is equal to our size plus the alignment minus 1. So that was the first step that we had to do. Then this bit is all fine and we get our pointer to the memory back. And then this is the point where we need to make sure our pointer is aligned. So how do we do that? First thing to do is, let's see here, we want to get the value of our pointer. So we're gonna call this pointer value and we'll just cast our mem pointer here to a pointer diff t to get the numerical value of the address at which it's pointing. Okay, then we need to figure out our offset. So for that we use our calculation that we were just looking at a few minutes ago. We got our alignment minus the pointer value bitwise ANDed with the alignment minus 1. Okay, so we've got our offset. Oh, and now we actually need to increase the pointer value by that offset. And then what we need to do is make sure we've increased our pointer value by the offset, and now we need to cast the pointer value back to void pointer because that's what we need. So let's see, it's equal to okay, so we've increased it by the offset, so it should now be aligned. We've cast it back to a void pointer, and then we set all the memory to zeros, and we return our memory. There's actually an issue here that we shouldn't be setting the memory before we have moved the pointer to point at a new address. So we should first set the memory to 0 and then put it in the wrong place again. Let's move it to here before we do anything. So we set all our memory to 0, by the amount that we need, and then we calculate the offset and move our pointer to point at an aligned address. Okay, so the next issue that we talked about was when we deallocate, we need to know by how much we are offset and move back by that amount. This isn't actually a problem in the per frame allocator because, as it says here, we don't need to do anything in this deallocate function. We just free all of our memory in that massive chunk at the end of the frame. So we don't care about this offset. But it is a problem when it comes to the OS memory allocator. Now, for the OS memory allocator, we don't really need, let's find this OS memory alloc that it calls into. We don't really need to align the data because in our OS memory alloc, we're making a call to calloc. And this will already make sure that our data is aligned to at least a boundary of 16 bytes, which should be okay for most cases. But just so that all our stuff works the same, we're gonna add in the alignment to this function as well. So I'll actually just pause it and fill in all this alignment because it's not that interesting to watch, especially when my computer is going so slow. So I've just moved the functionality we just wrote out into some functions, getting alignment information for getting the alignment, and align pointer for getting the offset and aligning the pointer, just so then I could use that here in our per frame allocator, and then also in our OS memory allocator here. Get our alignment information, allocate that amount of memory, and then align the pointer and return that pointer. So, as I was mentioning, the freeing of the memory and not knowing the offset is not a problem for the per frame allocator. But if we're doing this alignment in the OS memory allocator, it will be, because when we come to free the memory, our pointer will be pointing, or maybe pointing not at the start of that memory that we originally got. So to fix that, what we need to do is, in the memory that we get, we need to, in one of the empty bytes that are just padding bytes, we want to store that offset. So we need to make sure we actually have enough bytes for that, so we need an extra byte. So in our alignment information, we'll just take off that -1, so we definitely have one extra byte that we can store this offset in. And then we're going to do this in our align pointer function. So I'll do that here. So we're going to get our void pointer mem that we got, and we will cast that to a uint8 pointer. So we're casting our void pointer to a uint8 pointer, and then we're going to -1 from that. And the reason we're casting it to a uint8 is because we definitely want to just move back by only 1 byte, and a uint8 will definitely just take up 1 byte. So when we minus the 1, it will just move back by 1 byte, whereas if we didn't specify that, it might move back by 4 bytes. It might take this as a 4 byte integer, and it might move back 4, which we don't want. So we'll cast that to uint8 pointer, -1. Okay, so we've gone back, and then we need to dereference that pointer and put our offset in there. Let me just check that I have. Okay, I think I have the right amount of brackets, so that's okay. So we're now storing our offset. Now when we come to free our memory, we want to go back and have a peek at that offset and find out what it is and move our pointer back by however much we need to. So let's see, in our OS memory allocator, what we'll do is, okay, here we're gonna create a new function. We'll say mem is equal to unaligned pointer, and we'll pass in our memory, our pointer, sorry, and then we'll go and create that over here. So unaligned And then basically we just want to do the exact opposite of what we did up here. First we'll actually just check and then we want to get our offset, so offset is equal to, and we actually can just do this again. So now we have our offset, we need to move the pointer back. So cast our memory to unity pointer again, just so we know that we're going back by the exact amount of bytes that we need to be, and minus the offset to move it back. And then we can just return that. Yep. Okay, so now I'm going to run a program and see what happens. One thing I actually just forgot that would be nice to do before we run the program is here in this reserve capacity function where we allocate memory for our array, we can now use our new alignment parameter and pass in the alignment of whatever our type is. If not, it would have just used the default of 16, but it would be nicer to use whatever the alignment actually should be. So now we'll try and run the program. So I've just run the program and we didn't have a crash. It's in the same configuration, release mode, without the address sanitizer on, etc. So yeah, our problem seems to be solved. I hope that was interesting, and thanks for watching.